Do you know how to design singly reinforced concrete beams? In this lecture, I will solve a worked example for singly reinforced concrete beams. Now the question is that, what does it mean by singly reinforced concrete beam? A singly reinforced concrete beam is a beam where we provide only tension reinforcement, which in most of the cases is at the bottom of a simply supported concrete beam. If you haven't watched already theoretical background of singly reinforced concrete beams, click on this side of the screen to come on over. Stick around until the end of the lecture to learn fully how to design singly reinforced concrete beam using a step-by-step process. Hey friends, if you're new here, I am Dr. Qureshi, a senior lecturer in structural engineering and design at University of East London. On this channel, we explore civil engineering skills and life skills to help us lead more productive, happy, and examined life. Now, in this example, we have to determine area of main steel. Now, remember only this sheet. Determine the area of main steel of the beam. The material properties are FCK is given and FYK is given. FCK is compressive stress of concrete and FYK is tensile stress of steel. The section is given. B is 275, D is 450, and H is 500. Most of the time, in reality, the section may not be given to you or may be suggested by architects. Then you perform the checks. GK is given 12 kilonewton per meter, QK is given, and the span is given. So the first thing first, we will work out MED. So first we will work out the design load. All right. The design load is going to be 1.35 GK plus 1.5 QK. 1.35 GK is 12 plus 1.5 QK is 8. This will give me 28.2. So MED will be equal to WDL square over 8. W is 28.2 times L is 7 square over 8, 172.7 kilonewton meter. Now we have to compare this one with MRD. If this moment is less than MRD 0.167, so 0.167 FCK BD square, 0.167 FCK BD square, 0.167 times FCK is 25, yeah, and B is 275 and D is 450. Now here everything is in Newton and millimeters, all right. 0.167 times 25 times 275 times 450 square. So this is giving me a really big number. So 232.495 to 10 raised 6.
Can you please repeat the first equation? MRD, sorry.
10 raised 6. Yeah, first equation MRD is 0.167 FCK into, I've taken this equation, all right, this one. So my writing may not be very clear because of electronic pen. So 0.167 FCK BD square. So FCK is 25, B is 275 from here, D is 450 from here. So if you put all these values, you are getting this really big number. Now this is in Newton millimeter. Now one of the mistakes that some students will do in exams is that they will compare this really big value Newton into millimeter with this kilonewton into meter. So they would always design it as a singly reinforced beam. But here is the catch. You have to convert this into kilonewton into meter. All right, this is a very big number. So if you are getting a very big number and if you are comparing with 172 or in hundreds, it means that you're making mistake somewhere. The units need to be converted. Here the units were in Newton into millimeter, all right, because everything was in FCK is in Newton per millimeter square, and then B is in millimeter, and D square is in millimeter square. So this and this will get cancelled. The resulting unit is Newton into millimeter. So that needs to be converted. So for that, you have to multiply this whole by 10 raised minus 6, which means that this will give you 232.495. I am saying 232.5 kilonewton meter. Now this is your MRD. Should it be designed as singly or doubly reinforced beam?
Singly.
Singly, because applied is less than moment resistance of the compression side. Now again, this has been done for you with a really, I think this is quite legible. The one, I can't believe that the same person has written this. I have written this on the paper and then I'm using the electronic pen. So my writing isn't that bad, but it's just electronic pen. So the same process I've just worked out earlier. So first ultimate load, then design moment, which is 172.7, and then moment of resistance, MRD, 0.167 FCK BD square, FCK is 25. This is the same thing which I've done. MRD is greater than MED, or MED is less than MRD, then you have to design it as singly reinforced. Means that if applied is less than moment capacity of the beam, of the compressive side, then we design it as singly reinforced beam. It means that compression steel is not needed. If this does not satisfy, then you have to add compressive steel. You can't just increase the size of the steel to make it work.
But in a situation where you're not given the dimensions of your RC beam,
yes,
right? So in a situation where you can decide that, couldn't you then manipulate the sizes of your tension steel to make a size suit you rather than?
You cannot manipulate the size of tension steel bars. The other way could be increase the size of the beam. Increase B or D. You can manipulate B or D. Does it make sense? So if you increase the size of D, then certainly the MRD is going to increase. Yes?
Yeah.
If the depth is not limited by architectural reason, by all means change the depth. And then we have to work out this coefficient. So you get the concept that if MED is less than moment capacity of the section itself, then we design it as singly reinforced beam. If it isn't the case, then we design it either doubly reinforced beam, or we manipulate the size of the beam rather than the steel reinforcement. All right. This was the design process for designing singly reinforced concrete beam. Just to clarify what does it mean by singly reinforced concrete beam, I will draw some pictures. So a singly reinforced concrete beam, if you have a rectangular section, so this is singly reinforced. This is the cross section of a beam. It's a rectangular beam. In singly reinforced concrete beam, you will have bars only at the bottom, tension bars. And in doubly reinforced concrete beams, you will have bars at the bottom and you will have bars at the top as well. And certainly you will have stirrup as well over here. But if you only have these bottom bars, then this is termed as singly reinforced concrete beam. But if you have these top and bottom bars both, then it is doubly reinforced concrete beam.
Would you ever get the situation where you have a steel section in the middle of the concrete?
Steel section.
Yeah.
Yes.
Not a bar, not like a bar, but actual steel.
Not a bar, but steel. Yes. You can have this kind of situation. So in what situation you can have this kind of situation? That would be steel concrete composite structure. That will not be reinforced concrete. That's not part of our course, but I'm just responding to your question. So you could have a situation like this, that you have a column, and inside the column you have
this steel section, and outside you just have this reinforced concrete. Okay.
Yeah.
So you can have this kind of situation. It is termed as concrete encased steel column. Okay. In this, what's happening is that you have I section, and I section is surrounded by concrete. And these types of structures, these are termed as steel concrete composite structures. And there are special provisions for these structures. This is one of my expertise as well, actually. We use Eurocode 4. Eurocode 4 is for steel concrete composite structures. So this kind of composite structure, you can have steel circular sections and with concrete inside, or you could have rectangular hollow sections, rectangular steel sections with, so this is your kind of rectangular steel section at outside, and inside it is filled with concrete. Okay, these are termed as CFTs, concrete filled tubes. Okay. And you can design them using Eurocode 4. All right, so there is a complete guide for designing these elements. Let me come back. Let me focus on singly and doubly reinforced. Singly reinforced means that you just have steel on the tension side. Means that if you have a simply supported beam, that means that the maximum bending moment is going to happen at the center, and the bottom portion of the beam will have tension, the top portion will have compression. Because concrete is really weak in tension, that's the reason almost certainly you need to provide reinforcement on the tension side. But on compression side, the tension side is the bottom one, compression side is the top one. On compression side, normally you do not need, in most of the situation, you may not need the reinforcement, but some of the architectural conditions may require you to design a section as a doubly reinforced concrete beam. Means that when the section dimensions are limited due to architectural reasons, it means that you cannot increase the section side. If the applied moment is quite a lot, which the given section size cannot deal with steel reinforcement, in that case you have two options. Either you can put compression bars, keep the same sectional dimensions, or you can increase the size of the section if architectural requirements allow you to do that. So there are two options. So in today's lecture, I'm going to complete the example for singly reinforced concrete beams. Now here you would say to me that if we have tension reinforcement, we have this stirrup or shear reinforcement, a ring, how do we hold this ring? So normally we use, if compression reinforcement is not required, we use very small diameter bars to hold the stirrup, but these are not required. What we are dealing with here is this part, the tension reinforcement, and in doubly reinforced you will have this bottom tension reinforcement as well as you will have this compression reinforcement. And because MRD, the moment of resistance of a singly reinforced concrete section, is greater than applied, that means that we can design this beam as a singly reinforced concrete beam. Now the key thing here is that you can see the dimension of FCK is 25 Newton per millimeter square. So B has to be in millimeters, D has to be in millimeters. The resulting unit is Newton into millimeter. So this is always going to be really very large value. Ensure that you convert this. This is one of the most common mistakes in exams, that people will not convert this into kilonewton into meter and treat this as kilonewton into meter, this very high value. Remember that whenever you are getting very high value for MRD, which is not comparable, it means that you have made some mistake. So here you can see that this value is really very high, but you have to convert this into kilonewton into meter. So that's why you divide it by 1000 and then divide it by 1000, means that multiplied with 10 raised minus 6 to convert it into kilonewton into meter. Now you can see that the value here is comparable with MED. MED is 172, MRD is 232. It means they are comparable. Here they are not comparable at all. If you consider this, it means that this beam is going to collapse, to be honest, and then you will always going to be designing it as a singly reinforced concrete beam. And then the next process is, once you establish that if a beam can be designed as singly or doubly reinforced concrete beam, then you can find out the area of tension and compression steel. But here, because we just have singly reinforced concrete beam, so that is the reason we will find out area of tension steel only, because that is the main purpose of singly reinforced concrete beam, that we just have tension bars. I will have to find out this coefficient K naught, which is MED over FCK BD square. MED is applied moment, and then FCK is the compressive strength, 275 is the width, and 450 is the distance from center of steel reinforcement to the top fiber. Okay, this is not the overall height of the section. Again, do not confuse overall height of the section with D. D is the distance from center of tension reinforcement to top fiber. And we find out K naught after that. And then we have to find out this lever arm. So Z is equal to D, to bracket 0.5, and these values. So simply put value of D, put value of K naught, then you will be able to find out value of Z, which is 393.7. Now remember that if you are getting this lever arm, if you're getting some kind of a strange value, you can see that overall height is 500, D is 450. So certainly lever arm should be, force should be somewhere here at the top and then at the center of this steel reinforcement. So that has to be less than 450. If it's coming out to be more than 450, it means that you have made mistake somewhere. So this is how you check it. It comes out to be 393, which is fine, which is less than 450. And then finally what you do is you use this formula, MED over 0.87 FYKZ, and you know how did we derive this formula. Now FYK is yield strength of steel reinforcements. Some students in the past, what they do is that they simply replace it here with FCK, which is not the case. I mean, here you have FYK. So FYK is 500, and then you have MED, which is applied moment. Now you have to convert applied moment into millimeter and newtons. Again, that's why we're multiplying it with 10 raised to 6.
Sorry, so will it give you the FYK value in the question?
Yes, FYK will be given to you in the question. If it is not given to you, assume it to be 500.
Okay.
But it will be given to you. FCK will be given as well. So FYK, again, because the denominator here is FYK is Newton per millimeter square, Z is in millimeter. So that's why moment has to be converted into Newton into millimeters. Always converted. Otherwise, you will get here a very small value like 1.02 or 0.002, which will not make sense. Okay,
Jared, why do you have to assume it's 500?
it is given here, and this is the, so if we draw stress strain curve for reinforcing bar, this is kind of steel grade. So normally the steel grade that we use for, this is stress, this is strain, steel grade that we use for reinforced concrete structures is 500 Newton per millimeter square. So this is the point where you will have yield stress. So this point is FYK, which is equal to 500. And then this point where maximum is happening, this is your ultimate, but we are not using ultimate stress here. Stress can be denoted by sigma or F. This is the grade of steel that we normally use for reinforcing steel in reinforced concrete. Similar to what we use for concrete. Concrete has got different grades. Like we use C25, C30, C35, C40, which is telling us the concrete strength. But steel, normally for steel, we use the same grade steel in reinforced concrete structures. This is the most common one. And again, this is given in the question as well, but I just wanted to tell you what it is in real life. So when you plot a stress strain curve, this is the yield strength of your material. So we worked out lever arm, then simply putting these values and putting value of Z. You can see that the unit for moment that we have used is Newton into millimeters. Unit for FYK is Newton per millimeter square. Unit for Z is millimeter. This millimeter and millimeter will get cancelled. Newton and Newton will get cancelled. Now here, if something is in denominator over here, that will be multiplied here. So the resulting unit will be in millimeters. So that's where we get this millimeter from. And then we have this AS 1008. Now we are using this 4H20 bars. Means that high strength steel 20 millimeter diameter bars, and we're using 4 of them. Okay, so now how can we find out this information? You can either find out information for H20 and find out its area and multiply it by 4, but I would suggest you use a table. So if you go back to the table, previous table here, and that will be given to you as well. So 4H20 bars. So if you have this 20 bar and if you have 4 of them, now what will you do is that you have this required area of 1008. Now you will look into this table and see that what can you use, what can you possibly use. So you can use this 20 millimeter dia bar with and 4 of them. So that will give you 1260. So the area that you provide has to be higher than the one which is required. Our requirement is 1008 millimeter square. So as close as possible, but not really very close. So I mean, certainly you are limited by this number of bars. And the other option could be, closest option could be that you could use this 3 number 25 bars, but it will give you quite high area. So the reasonable match could be this one, 1260. We try to avoid using more and more number of bars because these are the common bars. So 20, 16, 12, these are common bars, and even up to 25. 32 and 40, these are not very common bars. So I mean, check again local requirements to see that if they are available. So this is how you come up with the sizes. And the background to this is that we simply work out the area of these bars using formula for a circle, which is pi by 4d square. And then from here, you can simply work out the area 314, which is here. And then simply you multiply it with 4 to get this number.
Where do you use normally 30, 32 and 40 mil bars?
Do you use normally?
Where do you use normally? Is it bridges or?
Yes. So we normally use these 32 and 40, yes, in bridges where this heavy reinforcement is required. Yes, definitely. But the local availability should always be checked about these bars, about these 32 and 40, and about this 6 as well. Number 6 isn't very common.
Is these bars on tension?
Is it?
Is it in tension?
The bars?
Yeah.
Yes, this is a tension reinforcement.
What's
The one that we...
Is it a different table for compression bars? If you have one?
No, it's the same. It's a very good question, because steel is equally strong in tension and compression. This table is just giving us area of the bars. It's not telling us tension or compression. But the properties of the steel for tension and compression, they are same. Okay, so Fyk in tension, Fyk in compression is the same thing, because steel is homogeneous material, so their properties are same. But what this table is showing us, it is showing us area of particular bars, so that we can quickly decide that how many bars we should put inside a beam. Now once you have done this exercise, then hence provide 4H20. 4H20 means that 4 high strength tensile bars with 20 millimeter diameter, and AS1 provided. So this is provided AS1. The one which we got from the formula is the required one. The provided one has to be higher than the required one for it to be a safe design. And then you can see that we simply draw this sketch showing the dimensions and then showing 4H20. Always try to draw the sketch. It will ensure that you get 100% marks. Okay.
Thanks for watching. Don't forget to subscribe for more practical insights into structural engineering and beyond. Until next time, stay curious.